All right, hopefully everything should be working now. Hi.
Surprising in compare
Hi.
of the region. Hi, Adil.
Hey.
Hello.
Yes, in compare of the last years, this year is very warm, and we both had a terrible winter, full of snow, and summertime is very hot as well. Adil joined us. Good afternoon in Berlin, and hello, Dr. Sadepur again. And you can
Morning in
organize.
Canada, huh?
Yeah, 10 o'clock over here.
What time do you have now? 10 oh,
10 a.m.
10 a.m.
Yes.
Oh, so it's okay, yeah. Hello, Roman.
Hello.
Hello. Good afternoon.
Hi.
I think my
Yeah, your video is turned off.
let me turn it on. Yeah. That's okay with it. Yeah. Now it's okay?
Yep.
Yes.
Dr. Sadrpur, can we start for the presentation, or you have?
We wait 1-2 minutes. Probably
Okay.
a few colleagues of
Okay.
us will join too. Okay, then we begin. Welcome to everyone. Today we are here in order to hear and to see the presentation of Adil and Nikar, two students of data science and analytics of Seneca Polytechnic in Toronto, two students from two different generations. I can explain a bit about the background of this internship of Nikar and Adil. With the contact, they contacted me, I think, at the beginning of the year, and I thought it would be nice if they could work a bit on testing of generative AI, because as you know, at ITPower, we have already developed a systematic testing method for classic AI classifiers, probably extended ontologies, mainly contributed by Hans Werner, who is present in this meeting. And we know that the generative AIs are used very often in private sector, but also in the industry. And as a company which offers AI services, it's important to have some method here for testing generative AI. It was clear to us that no systematic method like Pion can be found here or can be invented here for the generative AI, but probably some ideas and aspects which could be for a thorough testing of generative AI. And the task was to consider domain-specific generative AI. This is our intention. It was not to invent test methods for the whole ChatGPT or so, but the domain-specific AI systems which are used in specific sectors and are based on large language models. And the presentation today is the result of Adil and Nika's work during this period of time. I found it very nice. The work has a very strong technical aspect, but also some ideas, some concepts, some features which could be used and probably developed further for a conceptual basis of testing of domain-specific generative AI. Okay, I would say we skipped the mutual introduction because Adil and Nikar, you two are students of Seneca Polytechnic in Canada. We know it, and all the audience here, I think we are 8 people at the moment, are the people who work at ITPower Solutions. Therefore, I would like to ask you to start your presentation.
Okay. Can you see our screen?
Yes.
Okay, perfect.
Okay. Good afternoon in Berlin to ITPower, Dr. Sadipur and other colleagues, and good morning in Toronto to everyone. And thank you for joining. I am Nikar, and this is my colleague and my friend, Adil. We are data science and analytics students from Seneca Polytechnic, and we completed our co-op at ITPower. Today, we will present Universal Bench, simple and practical approach for testing domain-specific generative AI. We will focus on the supervised case where there is no reliable benchmark yet and show how to build a small human verified test set, run it, and read the results. Thank you, Dr. Sadipur, for the invitation, and thanks to all ITPower colleagues for your time. If anything is unclear, please stop me, and we will also have time for questions at the end. So let's begin. Generative AI. What is generative AI? Generative AI is software that create new things, such as text, images, even code. One example of generative AI that we are all familiar are large language models or LLMs, which are trained on huge amounts of text. You have seen examples like ChatGPT, Cloud 3.5, and Google Gemini 1.5, and others. These tools can turn raw documents into clear answers or drafts in seconds, but quality and cost vary. So we need a way to measure and trust the results. Today, we all we will show how this tech works at a high level and why we built a universal benchmarker to test it. Domain specific means a model is tuned for one narrow field or workflow. On the right, you see examples like physics, mathematics, programming, language, sports, music, even legal or finance. These areas use special terms, formats, and rules. So general chatbot can miss details or breach compliance. In our work, we test one domain at a time using that domain's own documents and tasks. Then score the model on correctness, faithfulness, and completeness. Today, we focus on the supervised tests where no trusted benchmark exists. So, build a small expert-approved set and grow it safely with RAG. What is a large language model, LLM? An LLM or a large language model is software trained on lots of, sorry, my apologies. A large language model is software trained on lots of text to predict the next taco. Uh, by by repeating this prediction, it can write answers, summaries, and code. The model stores what it learned as billions of parameters, which are like internal settings. Some LLMs are general purpose and try to handle many tasks. Others are domain specific and are adapted to one field. For example, medical guidelines or legal documents. Uh,
Okay, so continuing along, I can talk about how these language models are actually trained. As my partner, mentioned earlier, language models, at least modern language models, are trained on billions, if not trillions, of these things called parameters. They have huge amounts of data scraped from the web that they are trained on. And the thing that this phase is called the pre-training. And this pre-training phase is where the language model learns to predict the next word in a sequence. So if you look over here to this diagram on my right, there's an input sequence here, cat sat on A. This is information provided by a user, and the language model has many hidden layers in between where a transformation happens and a final output word is predicted based on all the internal weights that the language model was able to figure out by looking through its training data. So that's what it does. It's essentially kind of a next word predictor or generator. And that is all done in the pre-training phase. If you want, you can also go further and do fine-tuning to turn a general purpose model into a more specific specialized model. And even on top of that, you can do some reinforcement learning where you deploy the model and you get people to interact with it And so you can customize its responses to fit like a chatbot, or to fit like a human being, or to make it respond in like a customer service way, to moderate its outputs, and these types of things. So these are the three main phases involved in training LLMs, and you can kind of think of it like baking a cake. This would be the foundation for the cake. It's the biggest part and probably the most important. The fine tuning is like the icing that goes on top of the cake. Would be nice to have, but not essential. And finally, the reinforcement learning is like the cherry on the very top of the cake. It's just something, extra. And now we should also probably talk about parameters and tokens. As we mentioned earlier, language models are trained with a lot of tokens. Modern language models generally go from a billion to up to a trillion in the case of GPT-4 or GPT-5, which released earlier this week. So these parameters are like settings. They're internal configurations or weights. And to give another analogy, if you think about a video game that only has two settings, the ability to move left and the ability to move right, that's only two parameters. And with these two parameters, you don't really have a lot of complexity that can come from the system. But if I just add another parameter, like the ability to jump, to go up as well, now all of a sudden the entire system becomes a lot more complicated. There's a lot more possibilities that are involved. And, with language models, this also holds true. The more parameters you add to the language models, the more it can predict, and the more it can generate as a result. And tokens refer to something else. They're similar concepts, but they're related to words, but it refers to something else. Tokens are the ways that sentences and words themselves are broken down for machine learning models to understand. So tokenization is the process of converting raw string data, raw text data, into numerical representations, because language models and machine learning programs work best using numbers rather than text like we do. So for example, you see this sentence over here. Today we're talking about large language models and benchmarking. This sentence is split up by highlighted region into various different tokens. So today is one token, the comma is another token. Over here, if you notice, benchmarking, one word, instead of being split into one token, is split into two different tokens. So there are different rules for how tokenization can happen, but essentially it just means that all of these different tokens are assigned a number. And this is what these language models use. Another thing to note is that as you increase the token count or the parameter count, generally that means your costs are also going to go up for running these models, and the latency or the delay time or the time it takes for processing is also going to scale. It's going to go up as you increase parameters or tokens. And so we should also talk about why it's actually important in the first place to benchmark a generative AI or a language model. My colleague kind of touched upon this earlier, but I'll add some more specifics. The reason we benchmark is to be able to evaluate and test. Simply having a language model isn't enough if we actually care about deploying it and using it in the real world. So if I have 10 different models, I need to know which of those models gives me the best accuracy, which of them gives me the best cost, the cheapest price, which of them is actually fast and usable in different contexts. Maybe in some contexts you care more about accuracy and you care less about speed. So those are like for bigger problems, longer problems. But in other contexts, in like real-time deployment, you care more about speed than accuracy, or any combination of these. So depending on that, you need to know which model to use, and benchmarking is the solution. It provides objective metrics to compare between different models, even domain-specific models. And so if we have a benchmark in place, we can even make improvements to our model, and we're able to track how those improvements actually help in our workflow. Without benchmarks, we'd actually be shooting in the dark. So these provide a light to work towards, so that we're not just aiming in the dark.
So why universal bench? LLM quality is not one size fits all. A model that writes strong marketing text can still miss a medical dose. Before we deploy any model, we need proof that it follows compliance rules, stays within budget, and answers correctly. Universal bench gives that proof when no ready benchmark exists. Concept uh, concept, it is a system that can test any domain-specific generative AI as long as we have relevant documents, and it does not require manual partitioning of inputs and outputs. Key features. It works in niche fields that lack reliable evaluators. It creates the test set automatically while a subject expert checks a small set for accuracy, and it reports multiple metrics that are meaningful and statistically sound. And a high level idea. We feed domain knowledge, create question answer context items, run several models on the same set, then display scores and costs in clear dashboard. This is why universal bench. Uh, this slide shows uh, what our project aims to deliver. First, test set generation. We take the real documents for the domain, clean and chunk them, and create the question, answer, and context items. If a trusted teacher model exists, it can draft questions and answers. If not, a domain expert sits a small set and the system suggests more with retrieval, then the expert approves them. We also track coverage so every section of the corpus is represented. The second one is benchmark execution. The agent runs the same test set against one more candidate models in a controlled way, logs every prompt and response, and records latency and token counts. For example, we can compare two vendors on the exact same cardiology questions. And third, evaluation. We score correctness, faithfulness, completeness, and efficiency. Then show results in a dashboard. This lets stakeholders compare models and drill into failure to see why an answer was wrong and how to fix it. Here are my friend Adil is showing on the diagram for you.
Yeah, so here we have just a visual representation of what my partner talked about in the previous slide over here. The three phases are mapped out on this illustrative diagram. Phase one is where we create the test set. This is the test set generation of the benchmark itself. And phase two is where we run the test environment with a benchmarking agent and actually assess the performance of various different, target domain-specific language models or generative AI. And then in the end, we have the evaluations reports where we have, tables and visualizations of the different performance metrics of the models to help us make a decision about which model to pick. And we're going to go through each of these sections shortly in the presentation. We're going to begin with document ingestion, where we actually take documents from across the internet, maybe even using internal company documents. We have to chunk those, put them into a vector store database, and then using that vector store database, we will iterate through all of the chunks inside and make a foundation model, a very good model like ChatGPT 5 or Gemini 2.5 Pro. Something that doesn't it's a general purpose model, and we make it go through the knowledge base. And after that, after it makes questions, we can use some refinement with human experts coming in and validating the questions, seeing if they're actually, relevant, if they're not hallucinations, not made up. And we can also check with coverage mapping to see if every single part of our initial source documents from over here was correctly represented in the test set. So once all of that is refined and generated, we can go to the benchmarking part where we actually run the test. The language model responds to all the questions. Everything is stored in a log, and the log file is then later evaluated for accuracy, faithfulness, relevance, latency, cost, and all of this. And all of the results are visualized and put in tables.
And in this slide, show where our benchmark gets its content. First, public scraping. We pull approved guidelines and pages from selected sites, respecting licenses and robots rules. Second, internal databases, SharePoint, Confluence, and repositories. Everything stays inside the company environment. And third, user uploads PDFs, Word files, or text dropped in as needed. Every file goes through a quick permissions and quality check for license. PII, language and format. You can mix these sources to build a feature corpus. And this slide shows our first gate before any document enters the pipeline. We check four things. First, PII, personally identifiable information. We scan and mask names, IDs.
Sorry. What is PII? I missed it. Sorry.
It means personally identifiable information. So maybe things related to sensitive information. If you have a medical database, you don't want to just put your patient information on there, right? You want to mask it.
Okay.
Yeah, okay.
Thanks.
We scan and mask names, IDs, emails, and other sensitive fields or skip the file. And second, license. We verify that we have permissions to use the content. Unlicensed sources are not ingested. Third, the language. We detect the language, so we do not mix unsupported languages into the benchmark unless translation is approved. And fourth is the format. The file must be readable. We convert everything to clean and consistent text and skip any corrupted or unreadable PDFs. Catching issues here protects the whole benchmark. If the license is unclear, we skip the file. If we detect PII, we mask or drop it. If the language is not our target, we filter it or send it for approved translation. If the format is broken, we convert it to clean text or reject it. Every pass or fail is logged with a reason. Only clean, permitted, on-topic test moves forward. So the final benchmark is defensible and trustworthy.
Okay, so now I'll talk about chunking and context windows. First, we'll start with context windows. Every language model that we deal with can only take in a certain number of tokens, a certain number of word divisions, as we've talked about before. And for example, ChatGPT, I think, can take in about 128,000 tokens. Gemini 2.5 can take in about 1 million tokens. Some models have less if they're, local models. And depending on this, we need to, customize our approach to respect context windows and limits. Another thing is chunks. So we can't actually send entire documents for the next phase for text and vector embedding, because vector embedding only supports maybe up to 1,000 tokens, 1,200 tokens max. So we need to split up documents into smaller and more manageable chunks, because later we have to convert them into vectors, which we'll go into in a little bit. So after we've confirmed our source documents, we have to chunk the source documents, and then they get embedded into vectors, which we'll talk about now.
Embeddings turn each chunk of text into a high-dimensional vector of numbers. Meaningful passages land near each other in this space. So, for example, blood sugar sits close to glucose level. We compute a vector like in the shape you can see 0.6, 0.3, and that is a vector for every chunk, and each component is a number in this vector for every chunk, and store them in a vector database. When a question arrives, we embed the question to and search for the nearest vectors using cosine similarity or other ways of similarity, for example, Jacquard. The top K matches are the most relevant passages, which we feed to the model for RAG to ground answers and cut hallucinations.
A question.
Yep.
How does could you go to the last slide? The distance semantic similarity, how it is determined, the semantic similarity automatically?
We have a number of metrics for finding the semantic similarity. So once we convert the chunks into vectors, now they're just numerical representations, right? There are mathematical ways to find similarities between different vectors. One way is with a cosine similarity, or another way is with a dot product similarity, or as my partner mentioned, the Jacquard distance. These are different ways we can calculate the similarity between two different vectors. The vectors here just being one chunk and another chunk, and maybe your prompt, which is also converted into a vector.
Dot product in...
Sorry, but I do understand it right that you start with a certain embedding matrix. You need the embedding matrix from the sentence or text to the vector space.
Yeah, we'd use an embedding model to take our raw text data, and we would chunk that, and that would be converted into a vector embedding like this.
Yeah, and this embedding matrix or embedding table or embedding model that you used that you didn't develop by yourself, I guess.
No, we didn't make our own embedding model. We're using existing models like the
Okay.
ChatGPT small model, like the medium model by OpenAI, the open source.
Okay, you start with a fixed one, and then you can choose different distances on that target space. Okay, that's okay.
Yeah. You mean this one, right? The embedding model here.
Yeah, exactly. Yeah. That.
Yeah, we didn't develop our own. We're using open source models that exist.
Yeah. That is
Okay. And regarding the documents themselves, see over here too, we mentioned an embedding model that we would use. Like this is from OpenAI, text embedding 3 large. Whenever we create the chunks, we assign rich metadata to all of the chunks themselves, so we know exactly where our model picked them from. So maybe it came from this URL scraped from the internet. We assign it a unique ID. We give it a title, from, not we give it, but this is the title that the document itself was named. And maybe it has a page number, metadata to it as well. So we can find exactly where a chunk was from at any given time when it's used. And that's what this is about. And the benchmarking use cases, there's 2 of them. One of them is with back-to-back testing. If we already have a trusted teacher, like a trusted AI model that is good at domain-specific use cases. And another one, the semi-autonomous approach, which is what we're focusing on, is where we have a general foundation model, but it's not good for a particular field. So that's where we would have a human coming in to verify and validate outputs and generated benchmarks. So we use the semi-automatic approach.
Sorry. If you make a back-to-back test, you have text, generated text you have to compare, and you use for these metrics the embedding and then the distance of the metric in the target space.
You mean for how we answer the questions or how we make the benchmark?
Now, if you make a back-to-back test,
Yes.
you get two results. One maybe from the informed model or what else, and the other is from the let's say teacher. I don't know. So you have to compare the two answers, the two predictions. Is it right?
Uh,
Generated by the LLM or
right.
student or teacher or what else?
Yeah. So the teacher is the one that's generating the questions and the
Yeah,
answers. The ground truth is made by the teacher, and we would have
yeah.
a human to verify if the ground truth generated is accurate. And we don't use the RAG approach just yet. It comes in later when we're actually doing the benchmarking.
So my
Yeah.
question is the following. As I know, for me at least, the familiar term of back-to-back testing means that you two have a possibility to compare the two different outcomes. And in order to compare them, you need sort of a metric to say it's okay or it's not okay. I don't think that you will get always the same wordings as the outcome of two different types of models or what else. You understand what I mean?
Yeah,
You
I can
mean,
kind of
as Werner,
understand. Yeah.
how the difference
Yes,
between
I understand.
the outputs is determined? If you have the teacher is a reliable model, and you have the test object, you are going to test it, and your question is the evaluation of the comparison when you execute the test, and you have an output from your test object, how you or a reply from your student, how do you compare this reply with the reply of the teacher, the difference between them, how you measure the difference? Yes.
Yeah, that's exactly the question I have.
Okay, I guess we will come to this point in the phase of the evaluation.
Okay, okay,
Mhm.
okay.
So, for using case two in semi-automatic supervised, in some domains, no trusted model exists. When there is no reliable teacher model, we use a supervised test. We collect the domain documents, pass them through the quality gate, and have a domain expert approve a small seed of about 50 to 100 question answer items, each with a citation. The system then proposes new candidates from the same documents using retrieval. Each suggestion comes back to the expert for quick yes, no, or small edit, and every decision is logged. We watch coverage as we group. Heat map shows which sections are light, so the system favors those until the set is balanced. For example, in a diabetes carcass, the seed might include normal fasting glucose and a basal dose calculation. Then the system suggests a question on first line oral agents, and the expert tightens the wording and approves it. Once coverage is solid, we run the benchmark against several models and score accuracy, faithfulness to the source, completeness for multi-part answers, and efficiency in time and cost. This keeps the speed of automation and the trust of human review.
So here we just have a comparison between benefits and drawbacks of back-to-back testing versus just the semi-automatic supervised approach that my partner talked about just now. The teacher model here just refers to the foundation model that's used to generate the questions. In the supervised approach, we don't have a reliable teacher model, which is why we need human supervision on top. In the back-to-back testing approach, we do have the teacher model. And just to answer the question on evaluation, how do we evaluate if the answers or outputs generated by a student model or like the model we're testing, how do we accurately measure it? We use the teacher model to assess it, just as how language models assess pieces of text. The back-to-back testing approach is mostly autonomous, and with the supervised approach, because you have a human involved, there's more need for manual edits, so you have higher levels of human effort required for this approach, with the expert validation of the benchmarking test, and not as much for the back-to-back testing. And the ground truth itself for back-to-back testing would be generated by the teacher, making the questions, answers, and the context. This is the language model. And in the case of the semi-automatic testing, you would have to have a human expert review and assess. And we also have a tiering system for the kinds of difficulty levels of different questions. When they're generated by the teacher, we've split them up into 5 tiers. And these will come up later during our demo. And you see tier 1 questions are very simple questions, just defining a term, listing a set of things, naming something. Conceptual questions include a little bit more thinking. They need to compare concepts or summarize the whole idea. The tier 3 questions, we have labeled them as questions where you have to use logic to calculate or do some computations, derive something. Tier 4 is you get a hypothetical and you need to answer the hypothetical, and tier 5 is a more complicated prediction type of problem for extrapolation. And this is just an example of how the questions would be generated and like what kind of schema they would be stored in, with a question, answer, which chunk it was taken from, and what the context of the question is. So all of the questions that the teacher model generates would be from the source documents. Context is where in the source document it was taken from, and the question itself is generated based on the context. So is the answer. For this supervised approach with human, expertise involved, a human expert would review these questions and see if they're appropriate, and then accept them to be on the benchmark. So here we have phase 2 and phase 3. This is where we actually start the test, assuming that the benchmark is completed in phase 1. Now we do the benchmark, and then after that, after everything is run and logged, we see the performance report, and we see how well the different models actually compare.
And about the prompting style, prompting paradigm, prompting style changes results. So we test 3 styles. Actually, prompting is how we talk to an LLM. Zero shot, few shot, and chain of thoughts. Zero shot, no examples, just clear instructions to get an answer. Means we ask directly. For example, define basal insulin, fast and cheap for simple tasks. And in few shot adds 2 or 3 examples, question and answer pairs before the real question. This teaches format and usually improves consistency. Few shot just means I show the model a couple of examples, then my real question. For example, one question: what is normal fasting plasma glucose? the question one is what is normal fasting plasma and plasma glucose, and the answer is below 100 milligram per kilo. And example two is question: name two first line oral agents for type 2 diabetes. And answer is metformin and SGLT2 inhibitor. Now, the real question calculates the basal insulin dose for a 70 kilogram adult at 0.2 units per kilogram. But chain of thoughts ask for steps. Here is you can see in the slide a short chain of thoughts example. Question: what is 8 times by 9? Let's break it down. First, step one, then decompose. Think of 9 as equals 10 minus 1. Step two, plan. Multiply 8 by 10, then subtract 1 8 from that result. Step 3, compute 8 times by 10, which is 80, minus 1 8, which is 80 minus 8 equals 72. Final answer is computed as 72. In our benchmark, we run all 3 styles and report scores separately. So you can pick the cheapest style that still meets the accuracy you need.
So I'll talk about this. For the actual benchmarking agent, when we do phase 2, first we have to load the test inside to the testing environment, and then with the test itself, we also give a little prompt to the domain-specific model that we're testing, saying you're taking a test right now and you have to give answers in a specific format to make sure that we can easily evaluate it later on. So we want a JSON format that would be over here in the prompt, and then we would send this over to an executor, which is essentially just calling the model if the model is only available via API or something. That would happen during this phase, and the student represents the model itself. So the model finally gets the question and it answers the question. The question is logged, and even the prompt is logged along with the question. So you have the question, you have the answer, you have the type of the question, and so forth in the log files.
And result schema. Every API call ends up in this structure table. Question ID links the row back to the original question in the triple set. Prompt stores the exact text we sent to the model. Response is the answer. Adil, you can move the
response.
cursor on it. Yes, a response is the raw answer we received with no post processing. Latency records round trip time in seconds, so we can spot slow rounds. Tokens in, tokens out tells how many tokens we paid for, and cost converts those tokens into dollars using the provider's pricing. This log is the audit trail. It shows who answered what, when, how long it took, and how much it cost.
So once we go to the evaluation itself, there's many different metrics that we can actually assess the models based on. For instance, over here, the correctness, we could, just look at the semantic similarity between the model generated or the answer generated by the teacher and how the student model responded. We can do that. We can also take a look at the faithfulness. So if we have a RAG approach with our domain-specific model, we want to see how well it actually uses the database and the source documents to answer the question. And relevance is, well, did it actually answer the question? Did it try to answer the question? We can assess these types of parameters using a language model instead of just going purely by semantic search. And after this, we can check completeness. So maybe sometimes questions are multiple part, and some models, they only might answer the first part. We can check that as well to see if they're able to follow instructions fully. And we can take a look at the efficiency, meaning how long it actually takes to generate a response. How long is it? How much is the wait time? And then you can take a look at the cost, as we mentioned before. What's the dollar amount per 1,000 tokens? Or usually it's calculated by million tokens. And yeah, we can try giving the same prompts again, but just paraphrased a little bit, maybe introducing some noise inside, some stray words, grammatical mistakes, and we can see if the model can still respond, perform well. And we can ask the same questions again and see how the model responds to the same question to see consistency. And here's just an example.
Yep. Just there's this problem.
Yes, your question as well. You can.
Yeah, that's the correctness. Exact match and percentage. What does that mean exactly? That was the problem I had when I asked for the back-to-back test.
Yeah, so the teacher model generates questions, answers, and context. And when the student model, the model that we're testing, answers this, one way to check and evaluate the model is to what extent does it actually, match the answer generated by the teacher. You can go by a percent match, but this is not the only way.
Yeah. It is the syntactical comparison, you mean?
Yeah, it's not the only metric. We rely more on these types of metrics, but this is one. Yeah.
Okay. So you have two sentences, the one from the student, one from the teacher. Two answers.
Yes.
Yeah. What does it mean to have a percentage of exact match? This I really don't understand what you mean by this.
Okay,
Do you mean that there are, for, let's say, from 100 words, there are 90% the same? Or what do you mean by that?
We're taking a look at the meanings of the words that are being conveyed. So because everything is converted into vector form, we can compare the vector similarity of the words.
Yeah. Okay. So you map it into this, using this embedding into the vector space, and they measure the distance. And then other questions. Now you use Earth score, and you had for the embedding, you had the ChatGPT. I'm not quite sure. But what happens if you use different embedding methods, embedding tables?
We would have to keep the embedding model similar. We can't change the model in between.
Okay. So you fix them for the input and for the evaluation.
Sorry, can you repeat the question?
So you fix the embedding layer.
Yes.
For the input and for the evaluation.
Yes, we would have to keep that consistent because different models can generate completely different vectors for the same chunk.
Okay, that's okay. Now I understand. Thanks.
Okay.
Question: I don't know what is the BERT score. Is from the embedding model?
Yeah, this is a type of comparison that can be done to find the semantic similarity between two vectors.
Okay.
Just an example. We don't have to use this particular, semantic search similarity. We can use other ones.
You have a notion of difference. In this embedding space, you have a notion of difference. That's the important thing. Okay.
So over here, we just have an example of a possible dashboard that can be generated in the evaluation phase for a particular model. We can see very clearly how accurate the model is in answering the questions that were posed by the teacher. We can see how long it took to generate the answer, the cost for the generation in total, and the grounding score refers to if it actually used the sources from our internal documents to answer the question. And it didn't just make up the answers. And so we can also see a tier by tier breakdown of where exactly it struggled in, with a earlier tier questions just being define questions, name questions, and these ones being comparison summaries, and the final ones being like predictions, extrapolation. So we can see a tier by tier breakdown. And then in the end, we'd have a real-time dashboard that also has multiple models if we have multiple models, and we can compare them across each other with other types of graph and visualizations like radial charts or bar plots. And the log itself would be present in a JSON file to be viewed at in any form later. And we can use this to make some decisions about which model to make. We can have some insights on the dashboard. And we also have a live demo prepared that goes from the start to the end, or recorded demo, sorry, that goes through the entire pipeline from start to end, and we can show it to you right now. Just have it saved. I created some subtitles in German. Hey there, everybody. Well, do you have a sound? Can you hear the audio? Welcome to the pre-recorded section of... You can't hear the audio?
No.
Okay, 1 second, sorry. Let me see the share settings. Can you confirm if you have audio now? Hey there, everybody. Welcome to the pre-recorded section of our demo for the presentation. Hopefully by this point, we've already explained everything you needed to know in order for this demo to make sense. So let's just go over how the pipeline actually works from start to end with a practical example. We're going to take a domain, a specific domain, which is water engineering, and we're going to benchmark models that are fine-tuned to this domain. That's what we're going to do. So we need a general approach to benchmark things in this domain. And this approach, by the way, will work for any domain. We're just using this as an example for illustrative purposes to show you how the workflow operates. So the first thing we need to do is we need to ingest data. We need to create our knowledge base. If you remember, that is this part of phase one, document ingestion. And once we have the documents ingested from various different sources, we have to chunk the documents and send them over to a vector store database where they get embedded as vector embeddings. We use a text embedding model to do this, and I'll show you how that process works, but that is step 2, chunking and embedding. Step 3 is the teacher model generation, where we bring in a very skilled general purpose language model that is usually more costly to run but gives higher accuracy results, something like ChatGPT 5 or Gemini 2.5 Pro or Claude 4.1 Opus, the top of the line models. We'd use that with a RAG approach to go through the entirety of our vector database. We'd go through all the chunks, and by the time we're done, we'd have questions, answers, and context. Where did it get the chunks from? Where did it get the questions from? And we'd also have a difficulty tier listing, which looks something like this. We would have 5 different difficulty tiers, and we'll go into what all of these tiers mean in a little bit more. And beyond that, we have to do coverage mapping in step 4, which means we would need to look at the generated questions from the teacher model to make sure that the teacher model actually covered all of the stuff from the vector database, from our internal company documents, scraped documents. Everything we fed into the system needs to be represented over here. And over here, we're also going to make sure to do some human refinement of whatever questions and answers the teacher model generated. If needed, we can replace some things and we can exchange them with other prompts, other questions. So that's the human element of this, just to make sure that everything is going, well, at least until we have a reliable framework in place. And then the next phase after that is the student model testing, where we actually take all of the domain-specific, generative AI that we want to test, and we start testing them with the generated tests in steps 1 to 4. That is, if we look at this diagram, this step over here, where we go through all of phase 1, we generate the test set, we refine everything, and now the test set is there, the benchmark is there. Now we actually have to execute the benchmark. And the way we execute the benchmark is by sending the prompts over, by sending the test over to the benchmarking agent, which then prompts the target LLM, whichever model of choice, and you get responses back, and all of the responses are logged in a file. That is step 5. Step 6, of course, is the evaluation step, where we actually check the scores and the performances using various criteria and metrics like accuracy, the latency, the cost, and so forth of the different models that we've tested. And that is the last phase down here, where we get a report card, in table form, plus some visuals, some graphs, that are intuitive and easy to understand. Okay, now let's actually get started. First, we're going to start with the data ingestion where we can upload files of our own. For the purposes of this, I've already uploaded a couple of files. I've actually scraped them from the web, as you see here. We have the Comprehensive Hydrology and Water Cycle Textbook. We have the Advanced Dam Engineering and Spillway Design Handbook. We have 8 sources in total. I can add more if I want, like this from internal documents. Anything that I want, I can put in here. So you can also add a URL on here to scrape documents from a particular website, and you have the option to view the documents that were scraped, just the top snippets of what the documents are generally about. You can know what license they are licensed under. Are they public domain? Are they proprietary? Are they private? That type of information you can find out over here. You can get the link as well, of course. And now let's use this information, and we'll consider this our knowledge base. The next thing we need to do is to chunk it. We need to send it over to the vector store database, but before that we have to chunk it, and here we're going to do the chunking with 256 token size per chunk with a 50% overlap. So over here on the right hand side, you see for each of the 8 documents we've generated a number of chunks. These chunks are essentially just the document split up into smaller, more manageable components, as we've discussed earlier in the presentation. So document 1, Comprehensive Hydrology and Water Cycle Textbook, has been split into roughly 4 chunks. These highlighted sections are the overlaps that are in here. We have a little bit of overlap, that's fine. The reason we have overlap is to preserve continuity and context of the passages. So it's good that we have the overlap, and we have a token count on the top, of course. And on the right hand side, if we look, we have our vector database. For each chunk, we have a row on the database. So chunk 1, document 1 is this chunk represented by this row on the database. Chunk 2, document 1 is this row over here from this record over here. And we have it for all of them, all 36. And if you look over here, we also have the vector embedding generated for each of the chunks. So this chunk can be translated to this vector embedding. The vector embeddings, of course, have 1500 dimensions. We've just truncated them and only displayed the first 8 dimensions over here for simplicity's sake. But these vector embeddings essentially represent the entirety of the text in each chunk. This one for this vector embedding for this one, this vector embedding for this text chunk, and so on and so forth. We can use these vector embeddings on our machine learning models to efficiently and effectively find similarities between questions that we ask models and responses that we get. So now that we have that, we can go to the next step, which is creating the test set. So over here, we have a prompt that's going to serve as the system instructions that we're going to send to a foundation model, a very good language model that hasn't been fine-tuned, trained to water engineering in particular. It's a general purpose model, but it is the top of the line model. And we have some instructions that we're sending. And I'm going to zoom in a little bit so we can see. This is an example of the instructions we send to the teacher. You're a teacher model, and you're going to take in a set of chunks with IDs and text, and for each fact, represented in all the chunks, I want you to provide a JSON object that's essentially going to serve as a question-answer pair with context. So you have question IDs, which are unique, you have question texts, you have the question type, you have the difficulty level, things like this. Okay, and you have the answer as well, of course, plus maybe some grading criteria that can be added on later. So these are the rules, and if I generate, now you'll see that the model has generated 36 questions in total, roughly 1 question per chunk. And all of these questions are from the chunks themselves. Let's look at the first question. Define the term hydrology in the context of water engineering and explain its primary purpose. Now this question was actually generated by our teacher model by referencing the first chunk. That was from the textbook document, if you remember earlier, the water cycles and hydrology textbook that I showed in the previous sections of the demo. Now, this is directly from our source documents. And this is the question the language model generated, the teacher model generated, based on this information from the source document. And it also generated an answer, and I understand that it's kind of hard to see the answer here. We should fix that formatting. But if we click View JSON, we can view the entire answer over here. And I'm going to zoom in a little bit to see it clearer. So the answer is over here. In water engineering, hydrology is the scientific study of the movement, distribution, and quality of water on Earth. Its primary purpose is to understand the water cycle and predict water availability for various uses. So this answer that it generated over here not only answers the question, it also explicitly cites our source document in answering the question. That is why this is a good approach for generating questions using the teacher model with this RAG system. Now, the same thing has been done for all the other 36 questions, where if we take a look, for example, how might the introduction of aquatic weeds impact canal conveyance efficiency? That is answered in this chunk from the source documents, and the answer too is provided in the JSON right here. And one thing that I haven't talked about yet, or at least on this part of the demo, is the difficulty tiers. So these questions are not equivalently difficult. Some questions are more challenging than others, and the lower the number, generally the easier the question is. If you remember, I showed you this section that shows what each of the difficulty tiers mean. A tier 1 question is just a factual recall question, like a define question or a list question or a name the following question. Tier 2 is conceptual, where you have to summarize something, you have to compare two different things. This requires a bit more brain work. Tier 3 involves even more brain work with doing actual calculations, numerical computations, derivations, applying some logic. Tier 4 goes a step further and makes the logic even more pronounced. Now you have to do hypothetical situations. These are word problems. And Tier 5 is the hardest tier. These are complete prediction problems. They give you a set of criteria, and you need to answer this novel question based on those criteria. So that's that. Those are the difficulty tiers. And now that the test is generated, we can go to the next phase, which involves refinement and actually making sure that the entirety of our source documents are fully covered. Whenever you have a green mark over here for a chunk, it means all the chunks were adequately covered. In our case, it looks like every single chunk was correctly, adequately covered. So each chunk has at least one question associated with it, as you see here. So this chunk from document 1, this piece of information over here had a question generated for it. If we don't like the question that was generated, maybe we don't like the answer or we don't like the question itself, we can reject the question. And if we reject the question, it will not show up in the final benchmark. This is the human revision element. And also, imagine one of these parts was, uncovered. It said uncovered. If that's how it is, we can flag and resend it back to the teacher model to explicitly cover this chunk from document 4. Or document 2, my bad. So whenever you flag a chunk, it gets sent over here. You can flag multiple different chunks to be reevaluated by the teacher model. And at the end, you could have a benchmarking system that better covers all of the chunks from our source documents, or as best as possible. And over here too, we can see the distribution and breakdown of the different tiers of questions of the 36 chunks from our source documents. So 8 questions are tier 1 questions, which means they're simple questions like this, factual questions with define, list, name. 8 questions are tier 2, which are like conceptual questions. 7 are tier 3, so on and so forth. I think you understand the point. Now we can move on to the next phase, which actually involves benchmarking. We've so far completed phase 1. Now we move on to phase 2, which is actually starting the benchmarking test. So we go to benchmarks, and we have 3 different models over here that were trained via different methods. This one was a fine-tune of a specific general purpose model. This one was a specific model just exclusively trained for the purposes of this project and of water engineering, and this one is just using a RAG approach. So there are 3 different paradigms, and we want to see how each of these different LLM, each of these different generative AI, their domain-specific parts function. So there's also different testing paradigms where we can do zero shot, where we just give the question and expect these things to give answers, or few shot, where we give some similar questions and answers as examples first before we ask our own question to see how they perform, and then we have chain of thought, where we basically walk them through the reasoning and see how they perform on that for the different questions. For the purposes of this test, let's just go with zero shot. I'm going to select the Hydromine V1 model, and we run the test to see how this particular model performs on the benchmark that we created in steps 1 to 4. And as you can see here, the benchmarking agent goes through all of the questions one by one, and it sees the responses generated by the Hydromine V1. So this question was generated by the teacher model in step 3 over here. And this response is generated by the Hydromine model right here.
Now these responses are also graded, so far it looks like the responses that HydroMind has provided have been correct. Sometimes what can happen is, like over here, you get a partially correct answer because this is a difficult question. It's a predict a tier 5 question. Something in the answer may not be exactly what the teacher model wanted, meaning you get a partial evaluation, and at the end you can see that this model had an accuracy rating of 97.2. And you can also compare the other models in the same way. Let's look at StreamBot. This model, based on what we're seeing at the very top, is that it looks like it's not a very accurate model. It's getting a lot of these answers incorrect. And if we just read some of these answers, it looks like this is a very silly model. So, for example, given a region with high rainfall variability, recommend a suitable dam type for water storage and explain why. This is the question the teacher asked. And this is the response that the StreamBot model provided. A dam made of giant Lego blocks, so you can make it taller when it rains a lot. This is a ridiculous answer, so of course it was graded as incorrect. And there are some answers that got partially correct, but overall, incorrect, everything. And we have the accuracy of this model over here at just a shocking 8.3%. So the previous model, the HydroMind V1, performed much better at this benchmark for water engineering than the StreamBot mini model did. And obviously, the ability to compare various different domain-specific models in this niche is very useful. It allows us to pick the best possible models for our use cases, which leads perfectly into the next step, which is actually evaluation and scoring. So that would be phase 3 that we discussed previously in the diagram. Now you have a quality report card and you have the dashboard full of visuals. So in this section, we're looking at all 3 models, the HydroMind, AquaPro, and StreamBot model, and we're seeing how they perform. So over here particularly, we're looking at this radial graph, and it's comparing across 5 different parameters of functionality and performance. One of them is accuracy, which is how accurate the models were, like how many answers could the model get correct. The next one is latency, which is how long it takes to get a response, and then cost, which is how expensive it is to get a response. Grounding is if the model actually used the source documents to provide a response. And lastly, tokens is how many tokens did it generate, right? If you remember from earlier, tokens are like words, but they're words calculated in a special way. It depends on the tokenization rules that you use, but just think of them as words for this purpose. Now, the closer a model is to the edges of this 5-sided polygon, the better it performed. So if you look at this model, the blue one, HydroMind V1, it had the highest accuracy at 97.222. The next one in accuracy was AquaPro X, which only had 87.5, and the last one was only 8.333%, and that's of course StreamBot Mini with its ridiculous answers. Now, you can look at all these other parameters too, and this gives you a rough idea of which model to pick. Maybe if your use case is to get like a fast model, not the most accurate model, but a cheap, fast model, you probably go with AquaPro X, because look, it offers 87.5% accuracy. It's not terribly slow, it's faster than the blue model, HydroMind, and it's also pretty cheap, at least relative to HydroMind. It's also, giving grounded answers. So overall, this is a pretty balanced model. And just looking at this graph, you can assess that. And this breakdown over here shows the overall accuracy of the models. This is all of the models altogether. The average latency, meaning how long it took for them to respond, total cost for the entire benchmark test, and the grounding score, so how much they actually followed the sources. Now, if I look at just a specific model, maybe I just want to see StreamBot. StreamBot had only an 8.3% accuracy. It was pretty fast, it was pretty cheap, but it was not very grounded, which is the problem. And this is the tier breakdown. Surprisingly, it managed to get 16.7% of the tier 4 questions correct, maybe by fluke, but couldn't get any tier 2, tier 3 questions, or tier 5 questions for that matter. And here we have some of the top fail cases for areas of improvement for the model. This just gives you a good rundown of how poorly the model performed. Of course, if you want, you can also download the results as CSV files or JSON files to make it easier for display purposes somewhere else on a different application. Anyway, that concludes our demo. I hope it was informative, and just to make it very clear again, this is not only a demo that works for water engineering as a domain, it can be applied to work onto any domain. Great. Thank you guys for watching.
Very
that
interesting. Thank
concludes
you
it.
very much. Sebastian.
Tarek, du bist stumm, glaube ich.
Excuse me. Thank you very much for the nice presentation. I asked if anyone has any question.
I have a question, namely, how do you exclude that the model, due to overfitting, learns from internet public textbooks already the answers? I mean, if you argue that there is a reasoning, for example, computing 9 times 8 equals 72, it could be just learned without reasoning.
You mean if it's memorized?
Yeah, it's memorized, exactly things.
Yeah, so to prevent for overfitting, we'd have to carefully control the kinds of input documents that are, trained, like the model was trained on. And we can also ask questions that you were not seen anywhere else, like novel questions with particular proprietary documents in the benchmark itself to make the questions. So like, for example, are you familiar with Humanities Last Exam, that benchmark for generative AI? Yeah. Some types of questions too, it's very hard to memorize the answers for.
Yeah, no, from benchmarking with reasoning, where they used a dynamic generation of in math, generation of question answer pairings, so that they could measure it in that way. That and they see that there are these standard questions which can be which will be answered correctly by the models, and then they measure the discrepancy between the random generated questions and standard questions. Do you think also of some sort of randomization in your case?
You mean to procedurally make new questions, or?
Yeah, because you do not know whether the textbook, I mean, you looked at textbooks which were publicly available. So it is reasonable that it was already used for the learning of ChatGPT or other models. Yeah. So you need some sort of a randomization, I guess, in order to really see whether they do a reasoning or not.
Yeah, one method that we did suggest was to introduce intentionally errors in the questions of the benchmark.
Yeah.
So, add noise into it, make the words in an unexpected order, paraphrase questions. This can be done as an example.
Mm.
So you're using these robustness tests, so to speak, in order to differentiate whether it was memorized or really
Yeah.
reason.
Yeah, or if a question gives some variables, you can change the names of the variables, slightly change the numbers. You can do this.
Okay. Thanks.
No problem.
I have a question concerning the basis of the base of the information used by the both models, teacher and student. If you have a reliable teacher, it has a specific information basis. As you showed, some part of the information is from the public, from internet and so on. Some part are proprietary information from the own organization. And the student can be only compared with the teacher if it has the same information basis, right?
We can only check metrics like grounding if it has access to the same information basis, but we can still measure for accuracy even if it doesn't have the same information.
Mm-hmm. Okay.
Or using the semi-automatic supervised method, I mean, using the semi-automatic supervised method for using the case to.
Okay, in the first case, in the semi-automatic case, if you have no reliable teacher, you
Yeah.
make a teacher for your organization, right?
Yeah, we use a template.
Mhm. But I mean, in general, if, for example, our company has a project, has a contract to test the generative AI, domain-specific AI of a vendor, then we can apply your method if we know and use its information basis. It means we have to build a teacher, the benchmarker, and in order to have a reliable benchmark or a comparable benchmarker, we have to know precisely the information basis the vendor used for its AI machine.
Yes, if we want to specifically just see if the vendor can accomplish what they claim to accomplish, we need to have their information base. But if we want to test in general, let's say they're selling a water engineering model, as we discussed. If we just want to see the general feasibility of this model, we can take in information from all over the web and see how it performs. This is like a universal kind of benchmark.
Okay. Okay, thank you. The implementation you did is usable also by us, is open?
This is just like a demo. We still have to tweak some things like setting up the APIs for language models and embedding models. But yeah, it's meant to be an open workflow.
Okay. If the benchmarker is also an AI agent, we can use the same mechanism in order to build a new AI agent without the objective to test it. Is right?
We can build a new benchmarker even if we don't test anything. Yep.
Okay.
Without that objective. Yep.
Okay, thank you very much. I have a last question, sorry. How much work do you use in order? I mean, the chunks, the questions were proposed by some educated or model, I understood. But you have to evaluate that answer by an due to some expert. Is it right? Yeah.
I didn't hear your question fully. I heard something about chunks. Can you repeat?
If you, I understood in the following way: you have these textbooks or whatever, you chunk it,
Yeah.
and then you throw it into some educated machine, such that the machine gives you some questions and also some answers.
Yeah.
But then you have to evaluate the answers, whether they match to the question or not.
Yes.
And my question is, how much work is it? And you need some sort of an expert to evaluate it. How much work is it?
It depends on how many questions you're generating. So if you're generating 50 questions,
so around about for one question.
For around one question, I mean, generally you can just take a look at the context and you see if the question generated by the model matches the context and gives an answer. It also depends on like the field itself. Some fields very easy to verify, it just takes a couple seconds to read it. Other fields more complicated, like I don't know, quantum science, you need an expert to spend more time in breaking down the answer. So I'd say approximately maybe about for water engineering, for this case, about 15 seconds per question, you can verify it yourself to see if it, you know. But other fields, if they have elegant calculations, you have to do more.
Okay.
Yep.
Thanks.
Okay. No question more?
I have maybe a small question, if it's okay.
Yep.
Yeah, quick question, just for my understanding. So, you explained a few minutes ago that for accuracy testing, you don't need the same data distribution for the training of your student model. So, what you're implicitly, so just for my understanding, you're implicitly then testing something like robustness against distributional shifts, right? Because the distribution that you use for your test data to generate question and answers is different than the data distribution that the teacher model used, right? So the question that came to my mind is then, if you have this distributional shifts, how do you ensure that the distributional shifts in your data don't contain preferences for certain kinds of models and not others? Do you see where I'm going with that?
Yeah, I guess it would be how do you ensure like the bias in your model is not too high, such that it excludes other maybe correct answers, but not in its own training set. Other correct
I'm
answers.
I'm talking about the bias in the data, right? So the documents that you showed, for example,
Yep.
right? When you select the data that you're using for question generation, you have, in some sense, you have to ensure that the distributional shift that you have in that data is in some way not does not have any preference toward one model or the other, right?
Right.
That's
I think like the best workaround for a problem like this is to collect as much data as possible on a topic, so you have a whole breadth of information. The more information, I think you would have less bias, and also to choose your internal data for the benchmark. To choose those source documents using only reliable sources. Don't use random links. Use reputable links. I guess, like for example, if you're trying to make a model on astronomy, train things using NASA documentation. Don't train things using some random Google link, right? So even if it does have a preference for certain kinds of answers, at least at the end of the day, you know the answers are from a more reliable source.
okay. Thanks.
No problem.
Okay, thank you very much for the nice presentation and the nice work you did. I think we will be in contact in the future. And yes, I hope you much success, and probably we see each other in another opportunity in this similar to this meeting in the future. Thank you very much.
Thank you.
Thank you.
Goodbye.
Bye bye.
Bye bye.
Bye.
Thank you.